And hello, welcome back. So I'm going to just go straight into the details. I've explained in the last video what this block diagram does, and mostly it's based on this sub VI over here. Okay, it's based on this VI called Subsystem 2. Okay, so I will stop this. Okay, and save. I'll go to this subsystem and I'll show you what is the inner workings behind it. So this is of course a subsystem. Like I've shown you before, you can actually package a lot of complicated wiring into a subsystem. So this is what the subsystem is like. Okay, let's start with the very simple first. All right. This is the transfer function equals 1, so you can understand what's all this stuff on the outside here. Okay, so first we have a select transfer function type. All right, this is actually chosen by the user, chosen by you. Okay, of course I needed to actually wire it into this palette over here, this terminal. Okay. So to of course get your terminal, you have to click on this one of these white empty spaces and click on one of these variables to show, tell Labview which one do you want to control using an outside wire terminal. I've already explained to you how that works before in last previous video, so I'm not going to talk about it again. This behaves very similar to sub VIs. Okay. So this is a select transfer function type. This is the temperature in, and this is the power percentage control. So those are your inputs. Okay. And of course, power percentage control, I just multiplied by 0.01 over here because I want to change it into some power fraction instead of a percentage. So it's a bit easier to deal with, a bit more intuitive to deal with in the block diagram. Well, percentage is more intuitive on the front panel. It's not as intuitive on the block diagram. Okay, so that's why I'm doing that here. All of these are wired into a K structure. Okay, and notice all of this is a control simulation subsystem. That's why the background is yellow. Okay, so that's a K structure within this simulation subsystem where the power percentage control is there. The select transfer function type will determine which case to activate. I've already shown you how to do that. Okay, and the temperature in will be piped into this transfer function, but it will also be piped as one of the outputs. Okay, it will be piped as one of the outputs out of this key structure into this temperature in, and of course I also provide a combined waveform here. Okay, this waveform basically, I mean it's one way of getting a graph, but I guess this part is kind of redundant cause I've already done this two waveforms over here. Okay, I've already did a combination waveform over here so that we can see two signals on the same graph. Okay, this is done within the control and simulation loop. So in effect, this part is actually redundant as well as this. Okay, so this part is actually another way to get these waveforms. What are these waveforms? I just wanna superimpose the inlet temperature and the outlet temperature together in one graph. So that's what this is here for. Okay, so standard features, we actually have a build array, pipe this array into the sim time waveform VI, and that will actually give this combined waveform chart. Okay, the second output will be this temperature out. Okay, so I combine the temperature input and output into an array to plot it on a graph, but I also use that I pipe this output into a temperature out. Okay, so temperature in and temperature out are two of the outputs of this VI, of this VI. So all of them are wired over here. They are wired over here. So usually, I already showed you how to do it. Just click here, and then you click one of these variables which you want to connect the terminal to. Okay. So same as you would a sub VI. Okay. Of course, there's one more output here, which is the process power output. In case for the case of the Haber process mockup, so to speak, and the heater inlet and outlet. That's what's going to determine this process power output. For the rest of the transfer function, there's nothing really involved. So this is transfer function equals 1. We just pipe in the inlet temperature or input, and then it will be the same as the output. So there's nothing really there. And of course, I have this extra wire because I want to pipe out the input temperature as the output. So it's for easy reference. Okay, it makes it a lot neater as well when you want to plot graphs. Okay, so this is transfer function 1, first order with delay, shown you before. Transfer function comes before the transport delay. Second order, okay, the meso transfer function, multiple input, single output. So I just combine this meso transfer function, actually combines this temperature in with some noise from this signal generator. And of course, remember, you need to index the outputs, right? You have to index the outputs. Okay, now the heater one is a little bit more complicated, so let's go through it slowly. Okay, so let's start with the overall picture. I have some noise here. I have a power percentage control, and I have temperature in. All of these are going to be the outputs into this multiple input, multiple output transfer function. Okay, so this multiple input, multiple output transfer function. Okay, so what's this multiple input, multiple output transfer function going to give you? Okay, so first thing, it's the inlet temperature to the outlet temperature transfer function. So it's 1 over 2s plus 1. So that gives the pattern that if your inlet temperature is at 30 degrees and then you suddenly change it to 40 degrees, if the heater power is 0, the output temperature will also be 40 degrees, which should make sense. So there's a unity gain, a gain of 1, and then some process time. Okay, so that's how I connect input temperature and output temperature. Again, it should make some intuitive physical sense, but it's not based on any thorough reaction, thorough equation. Okay. So again, so the inlet and outlet temperature are controlled by a unity gain transfer function. The second one, so the top row actually corresponds to the temperature of the outlet temperature that I want to control. So the top one deals with the outlet temperature that I want to control. So inlet temperature connects to outlet temperature via some transfer function. Here is the heater power, so to speak, the heater power to outlet temperature transfer function. I just gave it a gain of 50 arbitrarily. Okay, so at when the heater is at 0%, there is no increase in temperature. When the heater is at 100%, there will be a 50 degrees C increase in temperature. That's all this thing is doing. Of course, you can have poles and zeros as you want, so those are pretty arbitrary as well. That's why I have a gain of 50, or the B0, the numerator first constant is actually 50. Then you have a coefficient of 1, just have a zero, a pole and a zero there. Now, to make sure that there are no oscillations, okay, the bottom is actually a second order sort of process, because of course electrical power will translate into heater power, A heater power will actually take some time to heat up the tank, and then have the output. Yeah. So the bottom, I have a second order process. It's actually 1 plus 3s whole thing squared. So that's 9s squared plus 6s plus 1. Yeah, that's what I have in this transfer function. So arbitrary second order process with 1 0 on top. And then I have a transfer function for noise. Okay, so it's just a 0.5 gain, that's all. At the bottom here, this will be the heater power output. Okay, I just randomly give it 1000 watts. So this second column here is actually heater power fraction, and it will translate to a temperature output and a power output. Very simple. So there's nothing too much to it. I just use this multiple input, multiple output to like just show you an example how it works. And of course, for this case, there is the inlet temperature will not affect heater power, and of course the temperature disturbance will not affect heater power. So both of these gains are 0. Okay, and I put 1000 because I assume the heater is 1000 watts. It can be more, it can be less, doesn't really matter. Okay, so that's how the model looks like. Okay, this model is going to put an array out. Okay, and there are two outputs that you need to so-called get, right? So the first output that you want to have, okay, the first output is called output number 0. Output number 0 is whatever transfer functions you have on your first row over here. Okay, that's output number 0. So remember that output number 0 is whatever transfer functions you have on your top row. So in this case, it's actually connecting whatever inputs to the output of the temperature output. Okay, so this transfer function will relate inlet temperature to outlet temperature over here. This is heater power fraction to outlet temperature, and then of course you have the so-called temperature noise to output temperature. Okay, so that's all this first row is doing. Okay, so this MIMO transfer function will give a what do you call that? An array that contains two pieces of data, two time varying pieces of data. The first is your outlet temperature, and the second is your heater power. So how do you know which when you index, right? You have more than one piece of data. How do you use this array index array to do it properly? So you pipe in your input into the index array function, and then you need to provide the index. So what's the index here? Okay, so remember your first row over here all corresponds to outlet temperature. So you can see over here there's this current output box. Okay, all of it is labeled as 0. So that means if you want and since all of this top array corresponds to outlet temperature, the index that corresponds to outlet temperature is 0 because it says current output is 0. If I want the heater, the heater power, I will go to the bottom row here. Okay, bottom row over here, and this index is actually number 1. So if I want heater power, my index I should provide is 1. So this one I want it to be outlet temperature. So this index array will have, you will need to give the index of 0, which corresponds to again outlet temperature. For this case, you have I want to have outlet power, so I give it the index of 1, just like what we were using here. It uses this number convention over here, so just be very wary. This is how it works in Labview. Okay, so once that is done, it will then have just one signal of a time varying output, time varying array or time varying signal that can be then piped to a temperature out kind of a thing. Likewise, over here, we can have a process power output here, and that's how this whole heater transfer function thingy works. Alright, so that's something you can play with around. Of course, Labview has more complicated examples as I explained before. So let me save this. Okay, so of course, Labview has more examples that that I showed you where to find before. So this is just something very, very simple, but it kind of wraps up everything that I was talking about. So if you select the heater, again, this is how it works. Okay, so apparently always this outlet temperature starts from 0 for some reason. Okay, I don't know why. Okay, maybe the initial condition is 0. I'm not really sure how to change, but I'm not going to try. Because it just takes a few seconds to actually adjust. And for my purposes, for the sake of this video, doesn't really matter. Okay, all of these things. So again, if I change the power percentage, it will start jump. The outlet temperature will jump. If I change the inlet temperature, the outlet temperature will also jump. Okay, so that's how this thing works. So I'm gonna stop. I want to do the more interesting one, which is the Haber process mockup. Okay, so bear with me. So I go through something a little bit more complex. It may overshoot the 20-minute rule I try to abide by, but it's pretty useful. Okay, so you know how the heater transfer function works already. There's a noise generator, there's a power percentage control, and all of this. Explained before how this works. Let's look at the Haber mockup. It's like, whoa, this is a lot more complicated. Alright, so what do we have here? Okay, what do we have here? It looks like a whole mess, this whole diagram. So let's break it down first, okay? Let's break it down. We have inputs again, a heater power control, a noise, and input temperature. Okay, so the noise is just temperature noise, nothing really to it. And this one has this power percentage control is nothing special to it. The only thing is that the input temperature, I kind of just add 300 to it. Okay, I just add 300 to it arbitrarily. Why? Because Haber process is actually typically carried around this kind of temperature. Okay, it's carried around this kind of temperature. So I added 300 to it, and I pipe this out as the temperature in so-called inlet temperature reading. Okay, so that's what the top line here is talking about. Okay, where does this inlet temperature go into? Okay, so all of these inlet temperature and noise actually goes into this outlet temperature transfer function. Okay, so this outlet temperature transfer function. So what do I have here? Okay, so heater inlet will be wired into this build array. So this first input will be the the tank inlet temperature, so to speak. It will be wired into this array as the first thing, and of course, as usual, it's a unity gain, and I just give it some arbitrary process time. Okay, so this is a first order process with some arbitrary process time, unity gain, that connects inlet temperature to outlet temperature. That's all this transfer function is doing here. The noise, I gave it a unity gain. This is the third input. Okay, this is the third input over here. Now what is this second input? This second input is actually connecting reactor power, meaning to say the chemical reaction is actually putting out some power. Of course, the chemical reaction plus heat supply actually puts translates to some increase in temperature. So of course, as your power increases, your temperature increases. So I just give you some again arbitrary gain. So maybe this is in kilojoule per mole or something, whatever. But that will result in a gain of 0.005 over some process time as usual, whatever it is. I didn't really care about the physicality of these numbers, but at least it will produce some graph with some intuitive you can get some intuition over it. Okay, so all of this is just fed into this multiple input single output meso transfer function, so that you can get the outlet temperature. And the outlet temperature is of course piped out here. Okay, so again, all these inputs, the reactor power, the inlet temperature, and the noise will translate to getting outlet temperature. However, as with a CSTR type system, the outlet temperature and the reactor temperature are exactly the same because it's a well-mixed tank. So if you are talking about this Haber process, where you try to generate ammonia via a reversible reaction, what will this result in? This means that the outlet temperature or the reactor temperature, this actually will affect the chemical reaction rate. Okay, so how do we translate that? Okay, first thing first, you need to when it comes to making a feedback loop, you need to use this thing called the memory VI. So memory VI is located in simulation, okay, under utilities. Okay, utilities, and then you see this memory thing over here. That's how you do feedback loops. Okay, like so. So temperature, reactor temperature is supposed to affect reaction rate. So that you can do by using this memory feedback VI or memory VI. So and again it's under simulation. And you go to utilities. Okay, so you see this memory over here. This allows for feedback. Okay, what this takes in, it is of course you basically feedback a loop. You feedback the temperature you want to feedback. Okay, so I take outlet temperature, I feed it back to the memory. Of course I do something here, but I'll explain this later. Okay, I feed it back, and this is what this wire here is. I feed it back here. The other input you need to give is some initial value, initial gas value. I can just leave it as 0. Okay, you can actually put in anything you want as your initial value. That's totally fine, but leaving it as 0 for this case is okay as well. So I didn't spend too much effort here. Okay, so what this does is that it takes the inlet temperature, outlet temperature, and feeds it back into another transfer function here. So what is this transfer function here doing? Okay, this transfer function is here to so-called represent the heat generation rate. Okay, this transfer function here is here to represent the heat generation rate. So what affects the heat generation rate? One is the temperature of the reactor. Two is, of course, since you have power percentage control. Okay, you have a power percentage control. So that will control the heat supplied to the reaction. So that can so-called double as a heat generation rate as well. Of course, you can add that in separately. That's fine, but I didn't do it here. Okay, thirdly, of course, you can have some noise. So I gave you the option of putting in a noise signal, but I just put it at 0 gain. So I don't have any kind of gain here. So this noise signal is connected to this transfer function to simulate some background noise. Okay, you can change the gain to something other than 0 if you want. Okay, So again, I wanted to signify that reaction rate will have inverse effect on temperature, because this is an exothermic reversible reaction. So as I increase temperature, my reaction rate should decrease, right? So I put a negative gain of 500, again very arbitrary, and a process time, also very arbitrary. Okay. All of these poles are also arbitrary. I just make it in such a way that all these are stable poles with no oscillation. Okay. Now, why did I put this minus 600 here? Okay, you notice I have a terminal that has minus 600 over here. What is this doing here? Okay, basically I wanted to set a reference temperature at 600, so that if my temperature is at 600, if my temperature is at 600, okay, it means that my my delta H equals to 0. So this is some equilibrium temperature. Your forward and backward rate are approximately the same. So it's just something I cook up. Okay, it's not really accurate with the actual reaction rate kinetics or whatnot. So there's a forward and backward reaction rate. Okay, so I just cooked up this number from arbitrarily, but of course I just referred to this table here from Wikipedia again, 600 degrees C. So that's arbitrary. But the effect is this. Okay, the effect is this. This is very important. Okay, so at 600 I want my. Okay, hold on. Yeah, at 600 degrees C, I want 600 degrees C to translate to a zero kilojoule per mole, or whatever units you want. Okay, delta H essentially equals to 0. Okay, delta H essentially equals to 0, meaning the forward and backward rates are at equilibrium. So if I have a transfer function of minus 500 over 2s plus 1, okay, what I need is the output, which is the ys, will be the transfer function multiplied into the input, right? Okay, so this input is what do you call that? It's the temperature, or rather the temperature relative to 600. Okay, because if I don't specify this, Labview will just take minus 500 and multiply it to whatever temperature I have, and that doesn't work out very well. Okay, so if my temperature is 10 degrees C, Labview will just take, if I have a 10 degrees C, okay, Labview will just take the 10 degrees C and multiply it into this transfer function, and then you'll get a very, very, very huge negative temperature feedback, which is not what I want at all. Okay, so what I'm saying is that when temperature is above 600, for example, if temperature is 650, okay, 650 minus 600, I will have 50 degrees C input, and when I put it into this input here, it will result in a negative reaction rate, or negative, it will result in an overall endothermic reaction. If it's below 600, 600, let's say, no, sorry, 500 degrees C, right? If let's say this thing's at 500 degrees C, right? What happens? Okay, so the Labview will take 500 minus 600, and it will get the result of minus 100 degrees C. So below and it's going to put this signal into here. So minus 100 times minus 500, that will give you a positive number. So for temperatures below 600, I have a net exothermic reaction. For temperatures above 600, I have a net endothermic reaction. So why did I do this subtraction thing here? It's to so-called give you that kind of effect. So for temperature above 600, you have a endothermic reaction, net. And for temperature below 600, you have a net exothermic reaction. So that's how all these things are modeled over here on the left hand side. And of course, that's why you have this subtraction thing here. Okay, so, and of course there's a heater fraction thingy. This is the second transfer function is the heater power fraction to the heater power output. Again, this is very random. So I just give it 1 times 10 to the 6. Okay, so it's a 1 megawatt heater or something like that. It's huge. So it's again very arbitrary, but that's what this thing does. Okay, so it will pump out a so-called reaction heat output rate in some arbitrary units. Okay, I didn't care about units here. And then I just pump it into this transfer function here, which takes 0.005 times the heater output, the heat supplied to this reactor, and then it gives it some process time. Okay, nothing too fancy. All right, so to get this heater power, okay, I just did this very lazy workaround. I just took whatever random number here and scaled it down arbitrarily just to fit the scales over here. Okay, that's what I did. Okay, so overall, that's how this whole system works. Okay, it's a very hand wavy way of doing things, but the important thing is that it shows you, you can use all of this simulation thing to actually simulate some processes if you want, some chemical process, some reactor process. In this case, we have some negative temperature feedback. Okay. So, you see, so the thing is that if I shut down this heater power, temperature is going to drop below 600. Okay, but below 600 the reaction rate is exothermic. The reaction is exothermic. So the outlet temperature is still going to be greater than the inlet temperature. Now if I raise the power all the way up, the heater power, okay, it's going to take some time to actually heat up the whole system. Okay, so and then now once it stabilizes, we can play with the inlet temperature so that you can see the effects. So the thing is, if I drop inlet temperature, if I decrease the inlet temperature, my output temperature will increase. The power output will increase, as you are seeing over here. You can't really see it in the power meter because it's very hard to see. Maybe I can reduce the heater power down, and you can see a little bit better. Okay, so I'm gonna wait for a while. Let's see how long it is. Oh, okay, 34 minutes. Okay, so over here we have more or less settled down. Okay, at some equilibrium level, more or less. So notice the power output is around 1135 or 11330. Okay, so again, all these units are arbitrary. I didn't pay any attention to them, but the effect is that okay, cool, we are almost at 600 degrees C. So that's a nice place to start. So let's increase the inlet temperature, okay, from 320 to 390. Okay, as we increase the inlet temperature, you look at the power output is actually dropping. Okay, the power output is actually dropping because the outlet temperature is also increasing, but so the power is dropping. So if I do it the other way around, if I decrease the inlet temperature, then the power output will increase. So there is some negative reactivity feedback here. Negative feedback here because it's a reversible reaction. So that's what maybe the Haber process is like. I don't really know. Okay, but that's how you do it on Labview. All right, all of these are uploaded onto my GitHub. Do take a look if you have time. Okay, that's all I'll be doing for now. Thanks for watching. I'll see you again. Okay.